You've dropped your keys, maybe your phone, we've all done it, right? It's just a part of life. But have you ever really stopped to think about why things fall? And not just why, but why they fall with such a specific, predictable acceleration? Well, today, we're going to pull back that curtain. We're going to derive the exact number for Earth's gravitational constant from the ground up.
So, here's the game plan. We'll kick things off with a classic thought experiment, then we'll nail down some key definitions, walk through the math step by step, actually calculate the value of g, and finally see how it all plays out in the real world.
Okay, let's start with a puzzle. A really old one, actually. It seems simple on the surface, but it gets to the very heart of how gravity really works. I mean, it's totally obvious, isn't it? You drop a coin and a feather, the coin smacks the floor, while the feather is just kind of floating its way down. So, heavier things fall faster? Simple. Case closed. Or is it? Well, the real story is way more interesting. You see, the real culprit here isn't an object's weight. It's something invisible, air resistance. Think about it. The feather has this huge surface area, so it's constantly bumping into air molecules, which slows it way, way down. The coin, on the other hand, it's small, it's dense, it just slices right through the air with almost no trouble at all. But here's where it gets really cool. What if you get rid of the air? If you put that coin and that feather in a vacuum chamber and drop them, they fall in perfect sync. They hit the bottom at the exact same instant. And that proves something incredible. Gravity is pulling on both of them in the exact same way, regardless of how much they weigh. And this perfect, idealized motion, well, it has a special name. To really dig into this, we have to start talking like physicists, and that means being super precise about what we mean. So let's get our definitions straight.
Okay, so this is it. Free fall is that perfect scenario we just saw in the vacuum. It's when an object is moving and the only thing pulling on it is gravity. No air resistance, no friction, nothing else. Just the pure downward pull of the Earth.
And here's the thing about free fall. Objects don't just fall at a steady speed. They accelerate. They get faster and faster, and the rate at which they speed up is constant. We call that constant g, the acceleration due to gravity. It's a specific number that tells us how much an object's speed increases every single second it's falling.
So, where does this number g actually come from? It's not just some random value somebody measured. We can actually derive it ourselves just by using a little bit of logic and combining two of the most important laws in all of physics, both from the mind of Sir Isaac Newton.
First up, we've got Newton's universal law of gravitation. This beauty of an equation calculates the force of gravity, that's F, between any two objects. Big G is the universal gravitational constant, M and M are the masses of the two objects, like the Earth and a rock, and D squared is the square of the distance between their centers. And second, we have his famous second law, F equals ma. But we're going to tweak it for our situation. The force F on a falling object is just its mass, m, times its acceleration. And since we're talking about free fall, that acceleration is our special value, little g. Now, here's the brilliant part. Both of these equations are describing the exact same force, the gravitational pull on that rock. So if they're describing the same thing, we can just set them equal to each other. One side tells us the force from the object's point of view, and the other tells us the force from the universe's point of view. And when we do that, look what happens. This is the big aha moment. Do you see the little m, the mass of the falling rock? It's on both sides of the equation. So it cancels out. It's gone. This is the mathematical proof of what we saw with the feather and the coin. The acceleration of an object in free fall has nothing to do with its own mass. It only depends on the mass of the planet it's on, m, and how far it is from the center, d. Just amazing.
Okay, so we've got the formula. We've proven the theory. Now it's time for the payoff. Let's turn this elegant piece of physics into a real, actual number by plugging in the values for planet Earth.
Here's what we need. We've got g, the gravitational constant, which is 6.7 times 10 to the minus 11 Newton meter squared per kilogram squared. We have Earth's mass, m, a whopping 6 times 10 to the 24 kilograms. And since we're talking about something on the surface, the distance d basically just becomes the Earth's radius, r, which is about 6.4 times 10 to the 6 meters.
So now all we have to do is pop these numbers into our formula. We multiply g by the mass of the Earth, and then we divide that whole thing by the Earth's radius, squared.
And crunch the numbers, and there it is, 9.8 meters per second squared. This number isn't magic. It's not arbitrary. It's a direct consequence of our planet's mass and its size. And what it means is that for every second an object is falling, it speeds up by 9.8 meters per second. That's like adding almost 22 miles per hour to its speed every single second.
All right, we've got our number. Let's wrap things up by looking at how we actually use this constant and talk about a few important details you need to know.
Now that we know the formula, we can ask a pretty smart question. If g depends on the radius of the Earth, what happens if the Earth's radius isn't, the same everywhere? And it's not. Our planet isn't a perfect sphere. It bulges out a little at the equator. This means if you're standing at the North Pole, you're slightly closer to the center, the radius is smaller, and g is a tiny bit stronger. At the equator, you're farther away, so g is a little weaker. And of course, the higher up you go, like climbing a mountain, your distance from the center increases, so g gets weaker still. These are tiny differences, but they're absolutely critical for things like GPS satellites.
The beauty of having this constant g is that it makes a lot of physics problems much easier. You can take the standard equations for motion and just plug in g wherever you see a for acceleration. And instead of a generic distance, s, we usually talk about height, h. It's a really handy shortcut for any problem involving falling objects.
One thing you have to watch out for, though, is the plus or minus sign. If something is falling down, it's moving with gravity and speeding up, so we say g is positive. But if you throw a ball up, it's moving against gravity and slowing down, so we have to use negative g in the math. And a cool little side effect of this is that the time it takes the ball to go up to its highest point is exactly the same as the time it takes to fall all the way back down.
And for one last cool fact to put this all in perspective, the value of g on the moon is only about 1/6 of what it is here on Earth. That's why you see those old videos of the Apollo astronauts taking those incredible, long, floating leaps across the lunar surface.
So I'll leave you with a final thought to chew on. Now that you know the formula, that g is all about the mass and radius of a celestial body, what does the moon's super low gravity tell you about its mass and its radius compared to our own planet? The answer is right there in the physics we just went through.